Hello everyone, welcome to Tactica Imperialis and to today's video. Today is going to be another one of my Tactica Tutorialis science lesson videos. In a direct follow-up to our lesson on work done last time, link in the description below to the playlist, we're going to be doing all about kinetic energy for GCSE science cum physics. Kinetic energy is one of those topics that comes up a lot. It is one of the very few formulas that is not given on any formula sheet in exams. It is a universal formula. You are expected to know it. You are expected to manipulate it. It comes up a lot, and it is very fundamental in many ways to what we do in physics. So what we're going to do today is we're going to recap work done. Follow on from that. I'm going to recap a little bit about what work done is, its equation, its units, and all of that sort of thing. Then we're going to look at kinetic energy as a concept, what it is, how we measure it, how we calculate it in a mathematical sense. And there will be a series of questions for you to do where you get to mess with the equation and work out the various variables. Once we've done that, we'll put the two lessons together. We're going to have a question which combines work and kinetic energy, and we may even go a little bit further than that, depending on how we're doing for time. Now, as with the work done lesson, this lesson was designed for a class that I'm teaching at a school, and so they're going to see the same clips that you do. At any point, if it feels like I'm not talking to you, the audience, if I make reference to PowerPoint slides or things like that, don't worry, that's because I'm talking to them and I'm not talking to you, the YouTube audience. Everything you need to know in this lesson is in the video. They're just getting a little bit of extra resource because it's a proper lesson for them rather than for you guys where it is a lesson, but it's also a video to entertain rather than the thing where you need to get PowerPoints and Word documents and all of that lovely stuff. So just wanted to caveat that if you get ever confused about what the heck I'm talking about, don't worry, it's just for a different audience. But I do hope you find this useful, and if you feel you need to go back to the work done video at any point, please do. If you have any questions, you can always ask in the live Premiere chat, and I will do my best to answer them as we go along. So without further ado, let us get started. We'll recap work done, and then we'll dive in full to kinetic energy. Let's begin. Okay, so the first thing we're going to do today is recap what we did last lesson, which was all about, if you remember, work done. As I say, link in the description if you need to remind yourself about any of that. So the activity I'd like you to do, I think you only need about 2 or 3 minutes to have a go at this, is I would like you to complete this thing, the equation triangle for work done, or the formula triangle, as you may have also heard. I'd like you to fill it in with the 3 symbols that go into it for the work done calculation. When you've done that, which should be hopefully not too difficult, I'd like you to give the name of each symbol and the unit for each symbol. So if that was, say, an A, you would say A equals whatever it is, and then you would give the unit, say, in brackets. So just to give you an example, it would be A equals something, 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 measured in something. Just lay it out like that, 3 columns, or 1, 2, 3, however you prefer, depending on what you're writing on. So give yourselves 2 or 3 minutes. I think you probably only need 3. Pause the video, have a go, and then come back and we'll go through the answers. Right. Hopefully you've paused the video and are now back to go through the solutions with a nice complete triangle, or at least the beginnings of a nice complete triangle and all the extra information. So the first thing is this up here, and this requires remembering our equation for work done from last lesson. So the triangle looks something like this. So work done up at the top, F as our left-hand side or our right-hand side. If you had these two the other way around, that is totally fine. You're allowed to have them either way around because it's a multiplication. But these two, F and D on the bottom, and the work done, the W or the WD, depending on which way you prefer to write it, up on the top. That is your completed triangle. If you haven't got it already, please complete it now. The names and units for these symbols are ones that, again, you've met before, and we'll go through them now. So WD, or W, I've just written it as WD to avoid confusing it with weight, is the work done. And that is measured in joules. Because work done has units of energy. It is an energy transfer. You might remember that from last time. It's not an energy store, but it is an energy transfer, so it gets the units of energy, that being joules. F, hopefully you would have got quite quickly once you knew that it was there. That is a force that is measured, as all forces are, in newtons. And D was the distance. And that was measured, it could have been in miles, could have been in millimeters or whatever, but generally we give our distances in meters. That is the standard unit of distance, is measured in meters. So just to recap how it would work, if I was to push this pen across the whiteboard, I apply a force and I push it over that distance, so I measure the force that I applied with my finger, the distance it traveled, multiply them together, and that would give me the work done. And that is the basic premise of what you need to know about work done. If you check the video from last time, we had some calculation practice where we got to manipulate this equation and use the equation triangle. So you want to work out work done, you want to work out force, you want to work out distance, all the different rearranging you need to do. We have a bit of practice from that in the previous video. Hopefully that wasn't too much of a tax and you've got that now as a set of notes either from doing it last lesson or doing it now. But we need to crack on and we need to have a look at kinetic energy. So, kinetic energy. You've probably heard the name. Now we need to start putting a bit of science to that name and then putting a bit of maths to that science. So, last time we talked about work done, we talked about the energy transferred when we move an object or we make a moving object stop. And the kinetic energy was what we sort of termed the fate, in air quotes, sort of a slightly dramatic term, but I like it, of work done. So when work done had been transferred, or when energy had been transferred as work done, it often ended up in the kinetic energy store. So the first thing we'll say is it's an energy store. And I'm then going to add to that and say that it is associated with, or you might say in slightly shorter terms, linked to moving objects. Moving being the key word. So if an object is moving, it has some kinetic energy, or it has, as you might say, some energy in its kinetic store. If you have movement, there is kinetic energy. The two go together like two things that go together very, very nicely. I'm sure you can come up with a better reference than I can. And it is very often where work done ends up. So work done usually transfers to, and I'll put in brackets, or from the kinetic store. So remember, work is done to move or stop an object. So work done is either when it starts an object moving, it's transferring energy to the kinetic store, or if it's stopping an object, it's transferring the energy out of the kinetic store into usually the surroundings as heat. Quite often if you slam the brakes on in a car, you notice the brakes got very, very hot. You'd certainly see that if you were doing like heat maps of Formula 1 cars, you'd notice their brakes were glowing hot because of the amount of kinetic energy that's been transferred into them as heat. The last thing to give you then about kinetic energy is its symbol. And the symbol, you might think as an idea, well, let's call it, I don't know, KE, capital K, capital A. Capital A, what am I talking about? Capital K, capital E. And you will certainly see that sometimes, but the symbol we're going to use, and the symbol I expect you to use going forward, is capital E, because it's an energy, with a subscript K. So we've got a capital E, and then if you've got the ability to go into the subscript button on Word, or just a little bit under, sort of under the line, you've got a capital K to show that it's kinetic, because we're going to meet lots of types of energy across this topic, and we need to differentiate them from each other, and this is how we typically do it, with what we call subscripts. So when we meet gravitational potential energy, that's got one subscript, elastic potential energy has another subscript, and the kinetic energy has another subscript, just to keep them distinct from each other rather than always writing E. And the unit, hopefully you should be able to guess this one for yourself. It is an energy, just like work done as an energy transfer. This one is an energy store. It is still energy, therefore its unit is joules. Hopefully that's not too earth-shattering for any of you watching at home. So they are the key points about kinetic energy. If you haven't already started taking them down in this sort of shorthand, or if you've got access to my slides then through them, please take them down now, put them into your notes so that you've got them. And if you need to add any explanation based on what I've been saying, feel free to rewind the video and go back and add to those notes with what I've been saying, because I appreciate I say a lot of words very, very quickly. So feel free to pause the video now, go back through and check anything you need to do while you take these notes down. Once you've done that, we will move on and do a little bit of equations so that we can see the maths behind kinetic energy. So, this equation I'm going to give you, and I'm going to put it in a ginormous box, and I thoroughly suggest you do the same, because this is one of those formulas, one of those equations that you're going to see over and over and over again. And in an exam, you're expected to know it by heart. It's not one that's given to you on a formula sheet, at least at the time I'm making this video. So, the equation for kinetic energy, E subscript K, is equal to 1/2 times M times V squared. I'm going to put that in a really important size box, because it's really important. EK is 1/2 mv squared. This formula, you really need to know it. I can't stress that one enough. But what are those symbols? What do they mean? Well, as we've already had, EK is our kinetic energy. We just gave you the symbol for that. And that is measured in joules. M is a symbol you've probably seen before as well. And M, in this case lowercase m, is mass. Now mass is not to be confused with weight, because weight is a force, mass is not. Despite the fact that we say things weigh certain amounts in like units of mass, our language is not always that fun. But this is mass, and we measure it in kilograms. Now you might be wondering, why not grams? Why kilograms? Honestly, I couldn't tell you exactly why the people who wrote the SI unit scale decided to make it kilograms. Probably because a lot of things are quite heavy, and so it would make more sense to work in kilograms than in grams. That's just my assumption. Now the final one is V. I'm not going to write V squared. I'm just going to write V. Now, when you think of kinetic energy, remember what kinetic energy is associated with. What is the store linked to? It's linked to moving objects. And so it stands to reason, I think, and hopefully you can sort of see where I'm going with this, that a moving object will have more movement energy, which is another way of talking about kinetic energy, if it is moving faster. So the faster something is going, the more kinetic energy it has. You might think of that in a case of, think about, I don't know, if you were to bump a football against a wall, if you kicked it really hard, it would have a lot of energy, and so it would transfer a bit more energy and come back with more speed than if you just kicked it really softly. That's to do with momentum, which is to do in usually a bit later in GCSE, but the faster something moves, the more energy it's got. You might also think about it if you're someone who's more inclined to catching a ball or generally getting your hand in the way of something, if you strike your hand, you might feel a little bit of heat being transferred from the impact, and that is the kinetic energy being transferred into mostly heat, but you'll also get a bit of dissipation into the surroundings as heat and sound, just like that. However, if you hit it really hard, like if you're saving a football being smashed from 30 yards that's flying into top bins, I'm sure at least one of you has done that, then you might feel that it actually is a lot more painful and or your hand is a lot more warm, that it's almost stinging. That's because there's been more kinetic energy transferred into your hand as heat, because you've still stopped the ball or the object, and so more energy has had to be transferred because the ball stopped, and so therefore more heat into your hand and your hand gets hotter. The faster something's going, TLDR, the faster something's going, the more kinetic energy it has. So V is the speed of the object. You may also see the term, I'm going to put this sort of underneath as a little comment, velocity, because you might be wondering why I've written V if it's speed, because in general we're talking about a thing called velocity, which is basically speed but also with a direction. Something you'll meet a little bit later on in life. I think it's still part of GCSE. You still see velocity, certainly at higher tier, so it's just introducing you to that term a little bit early. And speed is measured in, well, what do you think? Have a think. What do you think that speed might be measured in? There's probably a few of you at home gone miles per hour, because that's what our car's driving, or kilometers an hour. If your car is maybe of a different model, you might think kilometers per hour. And that's not a bad idea, but generally the speed is measured as an SI unit based on the other things that it measures. So speed is distance per unit time, because you've got miles per hour is distance divided by time. So the unit for speed is simply the two SI units put together, and we call that meters per second. Simple as that. So your equation, EK is a half mv squared, EK is your kinetic energy in joules, m is your mass in kilograms, and v is the speed or the velocity in meters per second. Now, the task that I would like you to do, first little task that we've done on kinetic energy, is I would like you to do a little bit of manipulating the equation. But before we do that, I'm going to give you the equation triangle. And how this one goes, I'm going to break up the half into its own separate thing. So we have a 4-part triangle. So EK is at the top, a half mv squared. So that is our equation triangle. And the task I would like you to do is rearrange the equation to solve for m and for v. So m equals what and v equals what. They're the two variables that you're also going to be asked to calculate from time to time, and you need to get a bit of practice at rearranging the equation. And there's a very easy trap to fall into, so I'm hoping that will be okay going forward. So 5 minutes at most, have a go at that and try and rearrange that equation with the help of the triangle to solve for mass or for speed. Off you go. Right, hopefully you've had a chance to pause and now you're back. So let's go through the solution, shall we? So first off, we need to remember how the equation triangle works. And what it means is whatever I cover up is what I'm solving for. So if I want to find kinetic energy, I would cover up EK, and then my triangle tells me I have to do a half times mass times v squared to solve for EK. Hopefully that's not too intuitive. We did see this with the work done triangle last time. Now, if I wanted to solve for mass, which is what we're going to do for our first one, I need to cover over, use those two fingers, cover over m. Now what is my triangle telling me to do? If I just put that over top, what is it telling me I have to do? Well, it's telling me to do two things. I have to have kinetic energy and do a division by a half times v squared. So you can write this in two different ways. So you've got EK divided by a half v squared. Or if you prefer to make that a little bit neater, you can pull the half across to be 2EK over v squared. Might look, I've done a little bit of magic there, because if I've divided by a half, that's equivalent. If you divide by a fraction, you flip the fraction upside down and turn it into a multiplication. So dividing by 1/2 is equal to timesing by 2. That's just a little aside. That's why I've been able to turn that divide by a half into timesing by 2 while still dividing by v squared. Then I asked you to solve for v if you could, and this one leads to probably one major mistake, but we'll address it now because I wouldn't be surprised if someone's walked into it, don't worry. If I cover over v squared, that tells me I need to do EK divided by a half times m in order to solve for v squared. So you might think, okay, EK divided by a half m. Done, right? Well, nearly. I'm going to rub this one out just to save myself a little bit of space. Because remember, if I cover up the triangle, I'm solving there for v squared. So this, EK divided by a half m, is equal to v squared. If I want to solve for just v, all on its own, I have to get rid of that squared. And the way I do that is by using what's called a square root. So there's a button for that on your calculator. It's this button right here. If you've got a scientific calculator like I do, it's this button right here is the square root button. So press that and type EK divided by a half m in there with the right numbers, and that is the way of solving for the speed. So I hope that was not too crazy. Now I'm going to give you a little worked example and we will get on, and you can have a go at all this stuff for yourself. Because I've been talking a lot and you probably want to do something now. So let's work through one question together so that you can see how we do this sort of thing. So let's say a 10 kilogram ball is kicked. Apologies for being a little bit stereotypical teacher, talking about the football. Apologies. Is kicked and moves, so I'll just call this EG, and moves at a speed of 5 meters per second. Calculate the kinetic energy. This would probably be a 3-mark question on an exam. Maybe 4 if you were asked to give the unit as well. In fact, we'll do that and give the unit. We'll do it as a full 3-4 mark question for a test. This is the sort of question you would see maybe worded slightly differently because some tests are a little bit evil. Now, I need to take out the information I've got in here, and I need to work out what I need to stick in. So the first thing, I need to calculate the kinetic energy. So I'm going to underline that and say I need to do EK equals. What formula do I need? I need that one up there, a half mv squared. That's the point. Got the right formula. If you've remembered the formula, that's a point. Then I need to find out what m and v are in this question. What is my mass and what is my speed? Well, it says that the ball is 10 kilograms, so my mass is 10 kilograms. Don't question the fact that my ball is 10 kilograms, okay? Most balls are nowhere near that heavy. That's 5 giant bags of potatoes. Then I need to work out the speed, and it tells me that in the question there. It might help me to underline these things when you're doing questions. V equals 5 meters per second. Then I need to stick that into my equation. So EK is a half times 10 times 5 squared point. And now we're going to go through that on our calculator together. So for a half, I'm going to do 0.5 because they're the same thing in decimal and fraction, multiplied by 10, multiplied by 5. And the squared button, in case you've never seen it before, is this one here. Hit that, get a squared, press equals 125 point. But I haven't got all the points yet because it's asked me to give the unit. Got to make sure to read the question carefully. If it says give the unit, I need to give the unit. And the unit, as we said, this is an energy, is joules. Point. Now, if you were solving this in full, you'd probably do it in a few more lines than 2 like I've done, but that is a full word solution to get you full marks in a test question or just in a general question. If you are struggling about how to lay out a question, this is the method I would advise. Now, coming up on screen in the moment, and also if you've got access to it in the other resources, is going to be a series of questions about kinetic energy. Some calculations, a little bit of practice at rearranging, and we're also going to do a little bit of unit conversion. So you might need to look up your unit conversions very briefly, but don't worry about it. They're not too difficult if you can just look them up. Have a go at the questions. Give yourself about 10 minutes, as we did in the work done lesson, to have a go. There's 4 of them. So have a go. Get as far as you can. Try and give the answers in full. Try and use the working as I've done. It might help you as well. And then when you're done, unpause the video and we will go through the solutions. Best of luck. 10 minutes. Off you go. Okay, let's go through some solutions, shall we? I hope that that wasn't too arduous. You were able to use the video to help you and all the work that we've done up to now. But let's go through the answers and we'll see how we got on together. So the first question talked about a car of mass 400 kilograms traveling at 10 meters per second. You see meters per second, you know that's a speed, so we can say V equals 10. It wants us to work out the kinetic energy. So we go back to our triangle or the box that we had earlier, we cover over EK, a half mv squared. So we need to do a half mv squared. Nice and simple. And we need to just plug our numbers in. Equals a half times 400 times 10 squared. Let's grab the calculator, stick some numbers in. 0.5 times 400 times 10 all square. To prove I'm not cheating. And you get 20,000 as our answer. 1,000. The unit for that, it's kinetic energy that you're working out. So the unit for that is joules. However, there was an option, if you prefer, to write it in shorthand, to give your answer in kilojoules, because we have 1,000 joules there, and each 1,000 joules equals 1 kilojoule. I'll write that over here for those of you who've forgotten, because I have talked about it before. Equals 1 kilojoule. So that's the conversion I've done at the bottom there. If you wanted to do it, 20,000 was absolutely correct, 20,000 joules, or 20 kilojoules. Both of those are correct. If you got that, your points would be awarded for right equation, right numbers, right answer. For the 3-mark question, we'll go something like that. Well done. If you need to make any corrections, just rewind through the method and write up the solutions in either another color or just underneath. Do not rub out / cross out / delete what you did the first time. It's worth being able to see the corrections you make so that you don't make the same mistake twice. Question 2. So we have a runner with a mass of 90 kilograms and they accelerate to a speed of 4 meters per second. Calculate the change in kinetic energy. So we're working out kinetic energy, which is a half mv squared. But the question's a little bit sneakier in that it asks for a change in kinetic energy. So you need to work out the change in speed. Now, you don't really need to worry about it for this question. All you need to say is that they speed up until they reach 4 meters per second. You may assume they're at a standing start. However, be very careful of questions that ask for a change in kinetic energy. I'll talk about this a little bit in a moment once we've solved this, but be very wary of the wording. So we just need to plug our numbers in again. Is a half times 90 times 4 squared, and we get times 90 times 4 square, 720, and the unit, of course, this is energy, is joules. So 1, 2, 3. I'm going to take a little aside to talk about change in here. So let's say, for example, that question had said that a runner is moving at 4 meters per second and accelerates or speeds up to 8 meters per second. So let's just think about that question. You might have it written down already. Or go back to read the question again. It says, instead of saying accelerates to 4 meters, that they start at 4 and speed up to 8. What is going to be the change in kinetic energy? Because if it says the total kinetic energy, that means that you'd use V equals 8, or as we've done here, V equals 4. If it asks for the change in, you would need to work out the change in speed. So it wouldn't be V equals 8, you would do V equals 4. You might want to make a comment about that on the side of your note where it says change in, so make sure you do a subtraction of the end speed and the start speed so that you can get that. In fact, I'll write that very shorthand here, just as a little aside for you if you're interested. Actually, not that. So change in speed means final speed take away what we call the initial or the starting speed equals V, not V equals final speed. Could write that as a caveat. So make sure you do always have that aware in your head. I'd advise you to take it down. Let's go through question 3 once you've done that. Right, question 3 is the first time I asked you to do a little bit of manipulation of the equations and a little bit of unit conversion. So we have a rocket of mass 800 kilograms, and they have a kinetic energy of 160 kilojoules of kinetic energy. So again, we've got that kilojoules. So we need to switch this into 160,000 joules because we're in kilojoules. If you've done it with 160 and not 160,000, then you'll get one less point. You get what we call error carried forward for making that mistake quite often, but you see a K for kilojoule, you need to times it by 1,000. Remember that. Then it asks us to work out the speed. So we need to go back to our triangle. Start off by V squared. So let's cover over V squared on the triangle. And it says that we need to do EK, the kinetic energy, divided by a half times M. Equals EK divided by a half times M. And that is equal to 160,000 divided by 0.5 times 800. Which is just 400, so we'll stick that in. So 160,000 divided by 0.5 times 800. So that gives us 400. However, we've only worked out V squared. So meters per second all square. If I want to work out V, this is the extra step you need to remember. V equals the square root of V squared equals the square root of 400. So that's that square root button. Push that, you get that symbol. I'm going to just press answer, but actually no, I won't. Square root of 400 equals 20. 20 meters per second. So your points there would be for correctly rearranging the equation, sticking in the numbers correctly. Then you'd get a point probably for 400. and then you get another point for 20. Be very careful with questions that ask you to work out speed, because there's a lot of pitfalls in remembering about your units being in kilojoules, about rearranging it correctly, and then about doing the square root. There's a lot of pitfalls in that question. So if you got that one wrong, I wouldn't worry too much, but make sure you practice it and understand and go over it a couple of times. Why have I got it wrong, and what do I need to do next time, so that when you get to any quizzes that we do, you will be better equipped to practice them. Final one then, question 4. Clear up corner, thank you. Question 4 says you have a boulder rolling down a hill from stationary and gaining 600 joules of kinetic energy, and it reaches a speed of 2 meters per second, and you need to find the mass. So we go back to the triangle, cover over M for a second, and it tells us I need to do EK divided by a half V squared, or a half times V squared, I suppose. So that is the equation you had to use, point. Then we need to plug the numbers in, equals 600 divided by a half times 2 squared. Make sure to square the 2. It could be easy to forget to do that. Point. Stick the numbers in. 600 divided by 0.5 times 2 squared. 300. So 2 squared is 4, times by 0.5 is 2, so 600 divided by 2 equals 300. And your unit for mass, hopefully you remember this one, you've seen it throughout the question so far, is in kilograms. So those are the 4 solutions you should have had. If you need to go and make any corrections and go back through, please do so now. Pause the video, wind back through, and go over the solutions, make any corrections you need to make. There's your last point, by the way. Give yourself a mark out of 12, because there's probably a 4th mark sneaking around in that speed question, but we'll make them all out of 3 for simplicity. So give yourself a mark out of 12. If you're feeling particularly bold, you can tell me what you got in the comments. I'm trusting you not to lie and cheat, because I think you're good. So that's the basics of kinetic energy. Now what I'd like to do for the last part of the lesson, before our summary little quiz, is to put it together with work done and combine everything we've done in these 2 videos together in one nice little bow. All right, so that is everything that I want to do teaching-wise as concerns kinetic energy and work done for today. But to finish off the lesson, I want to do a quick little summary of everything we've done over the past 2 videos, so that you are fully aware of the absolute basics of what you need to know, and you can then apply that to questions, including any homework that I have set you. So, split your board or your page or your document into a little table on 2 sides. Obviously, it'd be a bit tricky if you're doing this in a Word document, but there are 3 little challenges for you to do to finish off the lesson. On one side, I have kinetic energy. On the other side, I have work done. On both sides, I want you to write down the equation for them. I want you to write down here using either S or T, whether they are an energy store or an energy transfer. And then finally, I'd like you to complete the equation triangles for each of them. I've given you a start, but I've not told you how many segments the bottom part or the top part need to go into. So you're going to have to think about your notes, have a think about it, maybe look back through the videos if you have to, in order to complete this task. So you've got yourselves 4 minutes to finish this off. Good luck, and we'll go through the solutions once you come back. Right, welcome back. Let's go and sum all this up then. So, equation for kinetic energy. EK is a half mv squared. That is an equation, and I'm going to say it one more time, that you really need to know off the top of your head. We've done a lot of questions today that involved rearranging it to work out the speed or to work out the mass. So get yourselves comfortable with that as well, and you'll see a little bit of that in any upcoming homework. For work done, you might have just written W, but I've gone with WD. Force multiplied by distance. Remember what I said in the previous video on work done? You may see the D for distance written as an S instead. That's more of a general term, and you'll see that hopefully a little bit later on in life. But at this moment, use D. If you see S as well, don't panic. They mean the same thing. This question then, are they an energy store or are they an energy transfer? Well, kinetic energy, as I've said earlier today, is an energy store. So energy is transferred into the kinetic energy store when an object gets moving, or out of that store when it slows down. Work done, on the other hand, if you remember, is not an energy store. Energy is not stored as work done when the processes are over. Once work is done, it is transferred to a new store, a transit, a middle ground step that ends up in one of the energy stores. Quite often, the kinetic store, with a little bit of a side for surrounding dissipation as heat and or sound, which we did talk about in the previous lesson. And finally, the equation triangles. Do work done first, because this is from the start of the lesson, you may remember. Work done is equal to force times distance. That's just from the start of the lesson. We did that earlier. Kinetic energy is a slightly bigger triangle. EK on the top, and then we split it into 3. A half mv squared. You could theoretically say a half times m times v times v, but then you've got to have v's on both sides and it gets very, very messy. So I wouldn't do it that way if I were you. Keep it as that, as a half mv squared. So that is, in essence, work done and kinetic energy all summed up in about a quarter of a meter square on a whiteboard. So finish off your notes with anything. Go back through the video at this point. Go through the notes, add to them using what I've talked about or any supplementary resources you have. Make sure to make any corrections to the calculations that you've done to this point, and make sure you have a copy of the triangle, you have a copy of the equations, the units, and the information about energy stores and energy transfers. Right then everyone, that is the end of today's lesson, and I do hope that you enjoyed it and found it useful. That has been a summary of all things related to kinetic energy, with a little wrap up of work done from our previous lesson as well. I'm afraid there was nothing practical in it today, but if you want to do a little practical to test your knowledge at home, how about this one? So I have here my tape measure and one of my trusty bouncy balls that you will have seen from last lesson. The practical that I'm going to suggest to you, you're under no obligation to do this, but if you want to test your knowledge on kinetic energy, is find an object that you are comfortable dropping. So I've picked a bouncy ball. You may pick a miniature of yours. You may pick anything really that is not going to break or cause a dent when it hits the ground. Really, it's up to you. Pick something that's safe to drop, and probably a surface that's safe to drop it on, like a carpet, and drop it from, let's do it from, let's stretch it a little bit. Drop it from a height using your tape measure. I'm going to set mine to 1 meter. So my tape measure is currently set to 1 meter high. You see there, that says about 100. And with a lab partner, which may be someone you're working with at home, or if you've got really fast hands, you can do it yourself, but I suggest you get a partner. Take your object and time how long it takes to fall to the ground. So 3, 2, 1, drop. You might need a few attempts. You've got to think about working scientifically, so do some repeats, have a few attempts at it, and time how long it takes for the ball to fall to the ground. You can obviously do it from higher. If you're feeling confident, you want more time, you can do it from there. And from then, if you do the distance divided by the time, you can work out the speed. Pop one of these on a weighing scale or a balance, as they're officially known in science. You can work out the mass of your object and work out how much kinetic energy it has. If you're then feeling really brave, you can look ahead to gravitational potential energy and see if you can do some fun maths with that and work out the efficiency of your falling object. That's a little challenge for you if you fancy doing something practical with this. So, thank you very much for watching. I do hope you enjoyed the video and found the lesson useful. Next time, I'm not sure what I'm going to do. I have had a commenter request, as I mentioned in my previous video, for gas laws. So I'm thinking I might do gas laws at GCSE or A level. I'm also thinking of looking at momentum and collisions, because I find that to be quite a fun little topic. So I've got a few video ideas and I'm going to try and keep them coming at least on a weekly basis, maybe even get them up to 2 per week, because I'm really enjoying making these lesson videos and I hope that people are getting a lot out of them too, even if it's just killing 45 minutes of your time at 9 o'clock in the morning. Whatever it is that you get out of it, I do hope you're enjoying them and I'm really enjoying making them. So keep the requests coming and I will keep bringing you the content. For now though, thank you very much for watching. This has been Tactica Imperialis and this has been my Science Tactica Tutorialis lesson all about GCSE Kinetic Energy. Thank you very much for watching and I'll see you all again. Bye for now.